This is video number 10 now from Digital-University, where we're dealing now with various topics in linear algebra, and we're trying to kind of have a progression in what we're presenting. And as we do this, you're going to hear us more and more frequently refer to past videos that we made. And if you can go to the website, the playlist for all the videos will be there. All the videos will be there in their proper order. If you just found us on YouTube, they might kind of be scattered all over the place. Okay, in this video, we want to reflect upon some of our earlier comments concerning the two different types of square matrices, that is, non-singular and singular. In the previous videos, we pointed out that for the non-singular matrices, when you're going about trying to reduce them to row echelon form, we will encounter no free variables. They always have a unique solution, and the determinant is not zero. Well, there's one other fundamental property that they have, and in fact it's the essence of a definition of a non-singular matrix, and that is that its inverse always exists. So if we have a matrix A and it's non-singular, then there will be another matrix that exists. We call it its inverse, so that when we multiply it by its inverse, we get the identity matrix. And it turns out that this is really the fundamental definition of a non-singular matrix. And from this property, all these other properties follow. And what we want to do in this video is kind of get a firm handle on this. And then while we're doing that, it will also reveal the technique that we can use so that once we have a non-singular matrix, how can we go about finding its inverse? So that's what we want to try to take care of in this video. Now, in our earlier videos, this was a type of elementary matrix, a type 2 elementary matrix, and as you pointed out, this is a real simple example. This one has an inverse. So if I multiply it by its inverse, we get the identity matrix. And in this case, the inverse is real simple. It's just simply and then down here 0, 0, 1/3. So here's our matrix A. This is its inverse, and then we get the identity matrix. Now, to be clear, we said in past videos that if we have a matrix A and we multiply it by another matrix B, that's not the same thing as reversing the order of the multiplication. However, if we have the identity matrix, A times the identity matrix always gives us our original matrix A. And it doesn't matter whether we multiply on the right or whether we multiply on the left. It'll still give us the original matrix. Likewise, if we have a matrix like this and its inverse, then this times its inverse gives the identity matrix, or we could have it written like this, and we still get the identity matrix. I don't know if we pointed that out very well in the past videos, so we wanted to clear that up. Now, let's say that we have two matrices, A and B. They're both non-singular, so they both have inverses. What happens if we multiply the two matrices together? Do we still have a non-singular matrix? So let's say that we have matrix A. Try to get things in better focus here. We have matrix A, and it has an inverse. And we have matrix B, and this has an inverse. Now, if we multiply these two matrices together to get a new matrix, is this matrix also non-singular? Does this matrix also have an inverse? And the answer is yes, it is. It does have an inverse, and the inverse is, take this one, the second one, right at first, inverse, same thing for A. That would be the inverse of multiplying these two matrices together. And that's real easy to show. For example, if we have AB, and I multiply it by this, well, this, of course, is just the identity matrix. So now it's just the same as A times A times A inverse, and that indeed is the identity matrix. So we had two non-singular matrices, they both have inverses. Multiply them together, that new matrix that we get does have an inverse, it's this. Now, suppose that we have this, AB, and we multiply it by its inverse on the left side. Then we would have A inverse B inverse. And of course, this right here, this is the identity matrix. So that equals, and that's the identity matrix. So we have shown then that if we have two non-singular matrices, that is, you have two matrices, they both have an inverse. If you multiply them together, that matrix too has an inverse, and that's what it is equal to. Now suppose that we had a series of matrices. Say A1, A2, A3, all the way on out to AN. And these are all non-singular matrices. So if we multiply all of these together and we ask, what is the inverse of this? Then the inverse would be equal to this. That comes first. Then we keep going down the line. So finally we would have like this. It would be the inverse of each individual matrix, but you start at the last one becomes the first one, and then you proceed along. Okay, now what we want to show next is suppose that we have this kind of an equation. Try to get things in focus. Okay, we're here then. This looks very similar to problems that we have solved in the past videos. What we want to point out is we can rewrite the problem like this. We form the matrix just like we did before by taking the coefficients of the x1s, the x2s, and the x3s for those columns. There's the matrix. Now we multiply it by x1, x2, x3 in a form of what we call a column vector. And it equals the 0 vector, 0, 0, 0. This is the same as this. We can see that go across and down. So you have 3x1 plus x2 plus 0x3, that's what we have here, equals 0. So by using the rules of matrix multiplication, this is the same as this. And indeed, you can solve this system of equations and discover that if x1 equals 3, x2 equals -9, x3 equals 12, put those in there, these will come out all to be 0. Let's just take one. We go over and down. So we have 3 times 3 is 9. 1 times -9 is -9. That adds up to 0. 0 times 12 is 0. And do it like this. Again, do the multiplications, add them up, you get 0. Same thing here. Okay, sometimes then you see matrix problems written like this. We have a matrix A. And now we call this a column vector. And it equals another column vector B. In this particular example, our column vector that's equal to just happens to be the 0 vector. So we have A x equals 0. Well, what we want to say is this. If the matrix A has an inverse and it's multiplied by some column vector to give us the 0 vector, the only way that that can happen is this has to be 0. That's the only kind of solution that we can have. And it's an easy thing to show. We want to show it because it does have important consequences. So let's say that we have a matrix M. We're going to multiply it by a column vector x, and we want to get the 0 vector. And M has an inverse. Okay, if our matrix M has an inverse, then the only way that this can be 0 is this has to be 0. And it's easy to show. First step we can say is that this is equal to the identity matrix times this. For example, if we just had a real simple system, say a 2 by 2 matrix, A11, A12, A21, A22, and we multiply it by x1, x2 to equal 0, 0. Now this we can multiply by the identity matrix. 1, 0, 0, 1 times this that just equals x1, x2. Go across and down, we have x1, go across and down, 0x1 plus x2. So this is a legitimate way to write this, and we're doing it for a reason, obviously. So what we can say then is that this x equals I times x, but I is equal to M inverse times M. We said our matrix has an inverse, so of course M times its inverse equals the identity matrix. So now we have is that this equals this times this. But this is 0. That's what we started with. So this is 0. So what we have is this matrix, the inverse of M, times 0, that of course is going to give us 0. So what we've demonstrated is that here we have a matrix and it has an inverse, and if we have an equation similar to this one right here, where our matrix times a column vector x gives the 0 vector, if this matrix has an inverse, the only way that can happen is this has to be 0. X bar, our column vector, equals 0. So it's not a difficult thing to demonstrate, but it does have important consequences. So here then, the only solution that exists for this equation is for this to be 0. And why is that important? That's important because it means then here there's a unique solution. It's a trivial solution. X has to be 0. Okay, well for this matrix M, if we try to reduce it to row echelon form, what that means then is that none of the diagonal elements can be 0, because here we have our situation here. Our matrix, we're calling it A now, and A is non-singular. It has an inverse. We're multiplying it by the column vector, we'll just call it x, and it gives us the 0 vector. Okay, now, while we're reducing this to row echelon form by writing the augmented matrix here, if any of these diagonals come up 0, as you point out in the previous videos, that means we're going to have at least one row that consists entirely of zeros. What that means then is we're going to have some free variables cropping up. For example, here we have a 4 by 4 matrix. So if this last one here comes out to be all zeros because one of the diagonal elements was 0, then what that means is that when we get it in reduced form, well, this will have a lead variable for this row, this will have a lead variable, this will have a lead variable, but this row here that comes out all zeros, that's not going to have any lead variable. So that means that here then we're going to have a free variable because we have 1, 2, 3 lead variables, and from here we're going to have a free variable. In this case it's going to be the fourth element, the fourth number here. That means we're going to have an infinite number of solutions. We've gone over this now several times in our previous videos, but for our problem, the way it was set up, we don't have an infinite number of solutions. We only have one solution. This, all these components of the column vector x have to be 0. That's the only solution that exists. So that means that when we go about reducing this to a row echelon form, if we set up the augmented matrix, all of these none of these diagonals can come out to be 0. They all have to be non-zero numbers. And of course, that also means then we will have no row that consists entirely of zeros. Therefore, we have no free variables, only lead variables. Therefore, for the non-singular matrix, because it had an inverse, and because we have this, that means then for the non-singular matrix, no free variables, it has unique solution, and because none of the diagonal elements are 0, as you pointed out in the previous video, that means its determinant is not 0. So all these properties that a non-singular matrix has stems from the fact that it has an inverse and if it's set equal to 0, it has only one solution, a trivial solution. Now come back and join us in the next video. We're going to show we can use this information to analytically determine the inverse of a non-singular matrix. Come back, join us for that video, and we'll get that problem taken care of.